So good morning, everyone. I'm really happy to be here. My journey with Rust started probably symbolically in Paris in 2017 at Rust Fest. So now in Paris again. That's awesome. Something about me, I'm a passionate software engineer. That's it. Things I worked on: telephone business stations, JIT compiler, Mono projects, V8 team in Google, game engines, collaborative VR. And then I started working in Rust, first in blockchain something, and then operational research, vehicle routing. So I did lots of things. I'm just passionate about software. But that was me mostly professionally. Who am I for this talk? And for this talk, I am a man that has robotic competitions as a hobby. Actually, it's not just me. We have a team. You can probably recognize me. The boy up above me is my son. We are a bunch of friends that have fun doing robot competitions. And we are actually pretty good in Europe. We are winning lots of medals, so we really have a lot of fun. Talk outline. What are we going to talk about? Line followers, robots, and Rust. This is in general. So first about line followers and PID controller to control them. Then embedded Rust on an EV3 brick, which is an embedded system, and wrapping the CSDK to do things. Then the need for async to do things better and making async work on this kind of hardware. An embedded UI to actually see what the robot is doing and control the robot. And then the need for telemetry and data visualization to actually understand what's going on. And then advanced dial functioning techniques. So these are like two talks in one. You see robotic topics and Rust topics, and they are all mixed together. Let's go full speed and hope it works well. So talk progress. Now we are going to talk about line followers and PID controllers. Line follower robots, well, they follow a line on the ground. This you probably understood. There are fast ones, the one done with electronics, and they can do something like 6 meters per second on a straight line. They're engineering marvels. They're amazing. And then there are Lego ones, which is way, way slower. We can say overall 1 meter per second, and a totally different set of challenges because Lego is Lego. First, let's try thinking about a toy line follower. So we start with something simple. And the idea is that we only use two sensors, left and right. And if one side senses the line, go that way, because otherwise you would go out. Otherwise, go straight. And that's it. So let's start this thing up. Software doing controls, motor starting. Everything is supposed to be working. Yeah. And if I start it, you see that it follows the line somewhat. So it's going left and right. So, as I said, this is the toy version. This is something that probably, if you want to teach line following to a kid, you are going to do. Because it is easy, it's understandable. I mean, that works. But can we do better? This robot is binary. It has no concept of proportion. It doesn't react proportionally to errors. And how can we improve? That the first thing is to use sensors in an analog way, in a different way. Like, we have to set them up so that we can sense the line position very, very gradually. This is the sensor configuration. You see that the lights spot on the line where the robot can actually see it. And with this setup, we can have sub-millimeter accuracy. It's really incredible what we can do with Lego sensors if you are clever about positioning them and measuring. And about sub-millimeter. Here we don't have a fixed point unit, so we are going to do fixed point math all over the place in the code. Because, as I said, no fixed point, which means that the time will be in microseconds, and distance in millimeters with errors actually in microns, not because we have micron precision, that's because it makes sense with the numbers. And then speed in millimeters per second, which is the same as microns per microseconds. And actually, when measuring the rotational speed of the robots, I had to measure them in microns per microsecond because of the interactics. That was sort of crazy. Anyway, it will work. Now, about PID controllers. What is a PID controller? Has anyone in the stage already seen a PID controller? OK, not so many. So PID stands for proportional integral derivative. And the idea is that given the error E, which is the distance from the line, and 3 constants. There are 3 numbers, key P, key I, key D, PID. The turn, so the correction you are giving to the trajectory is a formula that is proportional to the error with a constant, to the integral of the error with another constant, and to the derivative of the error with a constant. And this should give a smooth control if the constants are tuned properly. Now, to understand it better, the proportional part, you see the robot. The robot speed is the blue line, so it's going a bit away from the line. The red arrow is the distance from the line, is the error we are measuring. And the idea is that the desired turn goes in the same direction as the red arrow, because you want it to go towards the line with a proportional constant. About the D part, derivative, the robot is turning, so it has a speed, which means that the line below the robot has an apparent speed relative to the robot, which you measure with the derivative of the error. And so what you want is to make a compensation for this thing, because in this case, you are already at the center. You don't want to switch away, so you have to compensate with the motors immediately. And about the integral, the idea is that if there is a turn, the robot is already rotating, that's fine, but the line distance over time is likely to have been always on the left in this case, because the line goes always on the left. And so you want to keep turning on the left more than what you would have done otherwise, intuitively. So the idea is that in a PID controller, you put everything together, the proportional, derivative, the integral, sum them, and the proportional considers now, the derivative predicts the future, and the integral takes the past into account, and everything works together to actually make the robot run properly. And that's fine, but wait, what about Rust? And we have been talking about line follower robots, algorithms, and trajectory control, but this is a Rust conference. So now, in the talk, we are switching from line followers to embedded Rust on this Lego brick. And why Rust in this kind of hobby robotic project? And you say, well, to learn the language. I actually learned the language this way back in 2018 to avoid bugs, because it's way better than C in doing these things, and because it's possible and it's fun, so why not? Rust on this specific brick. EV3 is this white brick that is the brain of the robot. The original firmware from Lego is fine, but bolting off other software on that is cumbersome. Let's skip this. There is another interesting possibility, which is EV3 Dev, which is actually a Debian port. So you can run a full Linux system on this brick. And it's extremely flexible, because you can do whatever you want. So you can write a Rust program, cross-compile it, run it there. The problem I had with this was unpredictable latency, up to 20 milliseconds of latency sometimes. And that was just unacceptable. And point is why? Why is latency an issue? And the point is that this, in a way, despite being a toy, is a hard real-time system. The PID runs in an event loop, and late results are wrong results. And the point is, how fast is fast enough? Because in a hard real-time system, it is not as fast as possible. It is as fast as needed. This is the actual definition. And so the line follower latency that we are aiming for, the blue arrows are the speed of the motor, and the other thing is the space you have to actually detect the hard turn. It's 20 millimeters. So if the robot speed is between 1 meter per second and 2 meters per second, in 2 milliseconds, you are going to travel from 2 to 4 millimeters, which means that with the line width of 20 millimeters, the max sensing period is about 4 milliseconds. If you are sensing the line more slowly than 4 milliseconds, you are going to do mistakes eventually, for sure. Now enter EV3RT. EV3RT is a port of an industrial real-time OS, which is called Toppers, HP, whatever, anyway, it's a real-time OS, on top of the EV3. It's an open source project, so fantastic. Doc and comments are in Japanese, because this is a Japanese project from a Japanese group for Japanese industry. Okay, the upside is it has a usable C SDK. So I have a hard real-time operating system running here thanks to somebody. I'm happy. And then Rust on this EV3RT operating system. Wrapping the C API is very, very simple. I'm not even going to spend more time on this because everybody should know. You just declare all C external functions which are unsafe, and then you wrap them with safe ones, because in the end, the API is safe. You're just reading numbers and writing numbers from sensors and to motors, so nothing fancy. Funny thing is that EV3RT has a dynamic program loader, and you actually need it, because otherwise rebuilding the whole firmware would be a nightmare. And the program are plain ELF files in principle, but the linker script to produce them is madness. And so I just couldn't reproduce this linking script, so what I did is this, the recipe. You compile a sample C application for EV3RT with a trivial main file, and you keep all the object files. Then the main files, we are going to throw it away. Then you compile the Rust code of your logic into a static library, which you can do with Rust. And then you implement the main function in Rust, all with Rust code. Then, of course, you replace the object file with the fake main function done in C with your static library done in Rust, and you run the original linker script. And it works. So it's terribly hackish, but it's reproducible. This is a toy project. I didn't want to do an industrial strength thing. It works. Be pragmatic. So the API that we have over EV3RT is simple. It is imperative, and that it can access everything. So we have access to all the sensors, every motor, everything. We can get the time in microseconds. We can sleep in milliseconds. This is a little bit painful. I would have liked more accurate sleeping, but fine. The OS latency is sub-millisecond. This works as intended. And also, I have simplified interfaces to file system and Bluetooth whenever needed. This is usable, but in my opinion, this is not enough. This is an API for Arduino style coding. The full logic is in a single event loop, like this loop. When you read the sensors, compute something, apply result to the motor, and you continue looping doing this thing. And what's wrong with it? Well, actually, nothing is wrong until everything is very simple. But when things get complicated, now we start switching from embedded Rust to why asynchronous Rust. You feel the need for async. One would be for concurrent sensor reads. Like sensor read rates have mismatches. Analog sensors here are 3 milliseconds. Ultrasound, which this robot doesn't have, are 20 milliseconds to be on the safe side. And a logic loop should read them concurrently, and then at their rate, and then react accordingly. The other important thing is concurrent logic. So this robot can be composed of different concurrent state machines, which do different things at different rates. Like you have to process the line error and compute the derivative integral, doing filtering for noise in the sensors. Then you have to process motor status and compute the wheel speeds. And then you have to run the driving logic and collect telemetry and handle screen input at buttons. So these are all different tasks. And so the API mismatch is here because the OS API is synchronous. It does not expose interrupts. So tasks, there are tasks, multitasking in EV3RT, but they are very cumbersome with no channels. It's literally like squaring a circle. It doesn't really work. But 1 millisecond latency is fine. So the idea is to make a very, very dumb async runtime. EV3RT does not expose interrupts, but it reads sensors concurrently anyway. It provides them in a shared RAM area, so we already have all the values. Now, the idea is to run an event loop where we collect all the data from pending reads, and we sleep at every iteration for 1 millisecond so that the thing has a pace of its own. And we implement future from the standard library from core without wakers, because at this point we don't need wakers. And this is actually the trick that makes it very simple. And we implement poll just by checking for new data and providing it when it is ready. And then we can compose futures with the usual combinators and macros and everything so that we get a root future. And at each event loop iteration, we just poll the root future, and this kicks every state machine into making progress, and everything works. So the event loop is this. It fits a single slide. It's incredibly simple. It is a function that is not asynchronous, takes a future as input, whatever implements a feature is pin boxed, then I will talk about that. It creates a dummy waker, which does nothing, so this is just boilerplate. And then in the loop, it does the update, which means read all the hardware data and put that into the EV3 data structure. Then actually poll the root future, and if it is ready, the program has ended, go away. And then apply whatever was decided from the logic and sleep 1 millisecond. And that's it. And this boilerplate, I don't want to comment it too much anyway, just no operation functions, the vtable for the wakers. This is just to implement a dummy waker that does nothing because we are not using that. At this point, the root task in the robot becomes a function like this, which it is async. This is the asynchronous function, the root functions that we were polling. And it does the initialization of everything. The setup is asynchronous because it will actually do dynamic tests on the motors and so on, so it needs to wait some time. Then it creates the tasks that are just things that give futures. And then it combines all of them with, this is zip because it is a small library, but anyway, it is like joins for futures. And then you have the combined future and you wait on that. And that's it. This is the full high-level logic as it gets combined with all the tasks inside. And so the main function that is exposed to the C side just creates the EV3 data structure for everything, creates the future, and then runs the thing with the event loop. That's it. So as you see, it's really, really simple. The pin boxed thing is because this thing has 64 megabytes of RAM. So I could have futures statically allocated, but then I would risk stack overflow. I didn't want to fight the possibility of a stack overflow. This thing is happening once per millisecond. An indirection in the function call is just nothing. I don't care. And so this is why I choose to actually add alloc support and use pin boxing. But it's because I was pragmatic in this context. So details on how it's actually working inside. The EV3 structure holds the full hardware state. It is not mutable. Its reference is shared everywhere. Now, how does this work? But the point is that every atomic piece of data, so every sensor value, everything, is enclosed in a cell. And this is fine because everything is single-threaded. So the Rust compiler will not complain. It knows what's going on, and it understands that there's no possibility to do mistakes, which is very, very handy. And every sensor future refers to the cell holding the data for that. And then it can provide either the current value immediately, because it's there, or it can support a waiting for the next, when there will be the proper update from the main logic. And it also can provide a stream of future values, which again is extra useful because then tasks can just communicate sharing these streams and reading from one stream, computing and sending it to another stream, which makes it really high level and easy to use and understand. So far so good. How do we interact with the robot? Because the robot, okay, we can write logic, but how do we give commands? And how do we inspect what's happening? And the idea is that we start now from going from async to an embedded GUI, a UI system. We really need a UI. So having a UI for the robot is useful, and the UI will look something like this. The challenge of making this, the EV3 screen has a resolution that is very small, hundreds of pixels, really small. The frame buffer layout is something that when I saw that, I would say, what ever going on. You can read it. It's monochrome, 2 bits per pixels, 2 pixels per byte, with 2 wasted bits per byte, which are there doing nothing. It's just insane. And it's not very big. It's totally 7 kilobytes. But the problem is that a full screen render, writing all the pixels, is really, really slow on this device, on this CPU. So this is unacceptable. And because we know latency is bad, we are not going to use the UI when the robot runs, but anyway, just using that is, we need to see the data in real time. And the graphical requirements we have on the UI is that we want to be able to write text, numbers, symbols, statically pick a screen orientation. This is because in other robots, the brick will be laid out in a different way. Should be easy to read when you're doing something else, so in action. And we should be able to draw bar charts in real time. That's the only real requirement. So the idea is to do a character-based UI. I self-designed the 18x18 square font, which is big and readable, so I can just use it. And it has another advantage. Square can be easily rotated, but most importantly, it does not cross bytes. Because it is 18x18, which is a multiple of 3, so essentially every write doesn't cross bytes. So it's very efficient to write. And the screen then can fit 10x7 charts, which is sort of enough. Now I can do regions on the screen to have different information in different areas. And if I would rotate the screen, I would still keep the same information, so that the UI logic is independent of the orientation. And at this point, to have a fast screen refresh, the idea is that a full logical frame buffer is just 70 bytes, because it is the 70 character that can be displayed. And double buffering becomes trivial, because the problem was speed, not memory. You have plenty of memory. And the diff between two screens is almost instant, because diffing to 70 bytes arrays, well, you don't even see it. And so we can redraw only the changed characters. And drawing each character is only a 54 bytes write because of the memory layout we picked. And then redraws, we can limit them to a fixed frame rate. And essentially, what we do now here is refresh every 25 milliseconds, because we are not going to see with our eyes faster than this anyway. So even if data is produced at a faster rate, the graphical controller task will update the screen every 25 milliseconds, and everything just works. We will see later in action in the other demo. So what's missing? Now we start switching from embedded UI to telemetry. What's missing is understanding what goes wrong. So you make the robot run, something strange happens, and how do you know? It is from UI to telemetry. Because a UI is fine, but we cannot use it while the robot races, because we cannot see the screen while the robot races. And we can film the robot, which is fine, but we don't know what's happening inside. So we really need a telemetry system. The things that we would like to inspect in this system are to have timestamps at microseconds resolution, to see the line error, to see the derivative of the error, how it was computed, the gyroscope data in degrees per second. This has a gyroscope. Then left and right wheel speed in millimeters per second. Left and right motor power that we are actually giving to the motor. This is the PWM frequency anyway, motor control. Then the status of the sensors, if they are seeing or not. And if it is not seeing anything, it is out of the line, in which direction it thinks the line is, which is important for understanding what was actually going on. And the overall distance the robot has run in millimeters. All of this, we can cram it into 20 bytes. So it's a very, very small unit of information. And the idea is that we want to see every decision taken, this 20-byte sample, potentially at about 1 kilohertz rate. So we should be transmitting 20 kilobytes per second over the Bluetooth serial, which with EV3RT while the robot runs. And I can tell you, this doesn't work. I've tried that. It's simply untenable. So the solution is to use offline telemetry. So in the end, the event loop runs at half a kilohertz for internal reasons, and 10,000 samples take 200 kilobytes of RAM, which we have plenty of. And at this frequency, 20 seconds, so 10,000 samples cover 20 seconds. And 20 seconds is a lot of time. So we just put each sample in the ring buffer while the robot runs, and we save the data when the race stops. And eventually we can reduce sample rates if we want to cover more time, but that's fine. So the telemetry task is very simple. It receives data samples from other tasks. It pushes the samples into a ring buffer at the required rate and saves data when requested, which is when the race stops. And this is what the telemetry results look like. It's done with Rust. Okay, I cannot really scroll, but anyway, you get the idea. So you get the distance traveled, the error, the derivative of the error, the gyroscope data, the intended corruption, the status of the sensors. It's very, very detailed. And so here you can really see what was going on, and if something strange happened, actually understand and correct the software. So now we are from telemetry to line follower control algorithms advanced. So first of all, the construction of this robot. This robot is made out of Lego, but is not the trivial line follower. There are a couple of nice things. One is it has also a gyroscope here, which is a Lego piece, a regular Lego piece, so that we also know the rotation of the robot in time, the rotational speed. And if you look below, you can see the sensors, but you can also see that it has 2 motors per wheel, which is a bit strange. This is because I wanted to have encoders to know the speed of the motors and the length traveled and everything. But these motors that have the encoders just don't work in races. They are too slow. These are proper motors that actually do work with races. They are directly connected to the wheels. And the other ones, they just help on the side without slowing the thing down. And they essentially use them only for the encoder. But, well, it actually worked out pretty well. And so since we have the encoders and the gyroscope, we can give it a stab at tuning PID parameters, because tuning PID parameters can be very confusing. You never understand what's going on. So we want a better way. We want to really understand how to give values to the PID parameters. And one idea is for tuning the key P, the proportional. Given a distance from the line, the red thing, which is the error, and given the robot direction and its speed, the intention is that the robot follows the direction of the green arrow. And if you look at the arrows, there is a known angle between the blue and the green. So the idea is that you need to give power to the wheels so that the instantaneous center of rotation of the robot will be so that the direction will be done of the green arrow. This is a mathematically solvable problem. It's solvable analytically. It's very easy. So the constant key P, you can actually figure out its range with this kind of calculation. Then tuning the derivative. The ideal is that you should be tuning for 0 rotation. In this situation, when you are on a straight line, if the robot has a rotation speed, the blue arrow means it is rotating towards the right. Then the apparent line speed is the red arrow. And the idea is that the desired compensation should be big enough to make the speed 0. And on a straight line, you can actually use the gyroscope, which is way more reliable than the derivative, and just tune for 0 rotational speed. This only on a straight line. And tuning for smooth turns can be pretty tricky, but the idea here is consider rotation speeds. There is the actual rotation speed in blue. We take either from the gyro or from wheel speed. This is the actual rotation speed of the robot. And now it is going on the left because it is turning. There is the apparent rotation speed given from the derivative. This should be 0 in theory because we should stay on the line, which means that the desired rotation speed is the difference between the two. Again, this is a bit of analytical mathematics and geometry, but it can be done, and so you can have a clue how big the constants should be. So at this point, let's have some fun, because we have explained a lot of things, and this thing should be running, hopefully. Second setup. Will it run? Okay, I think you can see the reaction time it has and how it's fast. Keep in mind that it's a toy. So this is an amazing result for a piece of Lego brick. So, a quick recap. We have seen Lego line followers, PID controllers, embedded Rust on a very strange RTOS on a Lego brick, a custom embedded async runtime to make things easier to program and more effective, a minimal and efficient telemetry system in this embedded system, advanced live following algorithms, also the UI we have seen. An important notice, no CRUB was harmed in the production of this talk, but several were put to good use. So the talk is done with PresentTerm, which is a Rust application to do presentation in a terminal. I'm using the West terminal. I'm running this on the Cosmic desktop. And in general, a very big thank to the community, because I'm using so many Rust tools in my daily life that really, thanks to the community, which means all of you, because you are the community, the Rust ecosystem is amazing for you. Thanks.